Imagine a world in which everyone used a different symbol for adding two numbers. What would happen if some people used this to represent addition, while others used this? How could you understand what an equation meant if the symbols for all operations depended on the language of the author? Standard symbols are essential for the cooperation and advancement of cross-cultural work. Just like the plus symbol represents an addition all over the world, circuits use standard symbols for parameters and components. It is in this way that a circuit designed in the US can easily be understood in India or anywhere else without translation. We will find many different components in electrical engineering, and each component will have a symbol that is standard across the world. Consider the case of a battery. How many different ways exist to draw a battery? Is it a AAA or a coin cell? What color is it? Moreover, how long would it take to draw a recognizable battery every time you need one on a circuit? We hope by now you can see the benefit of using symbols to represent components in a circuit. Let's look at an example. This is our 2-battery, 2-light bulb circuit from the first video. The symbol for a battery is shown here. Note that the positive terminal of a battery is represented by a longer line. The electrical behavior of light bulbs can be modeled by resistors. We will discuss resistors in depth soon enough, but for now take a leap of faith and believe us that light bulbs behave like resistors. This is a symbol for a resistor. Even though there are many ways to draw different types of batteries in light bulbs, when using symbols we will always have the same circuit drawing. Now the word of the day to impress your friends. A circuit drawing done with component symbols is called a schematic. From now on, we'll refer to these drawings as schematics. Let's go back to our hypothetical world and assume that we all had the same name. Can you imagine how complicated daily life would be? A similar chaos would exist if all components in a circuit had the same name. For this reason, all components always have a name that identifies them. Just like your name was chosen by your parents, components' names in a circuit can be arbitrarily chosen by the designer. However, some conventions are followed when naming components. For example, resistors' names are usually the letter R followed by a number, R1. Batteries are named by the letter V followed by a number, V1. You don't necessarily need to follow this convention, but most people in the world do. It is important that no two components in a schematic are named the same. Just like having two Toms in a class may be confusing, having two components named R1 could cause serious problems when working on the circuit. We can now add names to our schematic. When talking about a component within a circuit, we can simply refer to it by its name. For example, battery V2 is next to resistor R1. Components are not the only things in circuits that have names. In fact, every single parameter, like voltage and current, has a name. In our first video, we showed that the voltage between two nodes is named by the letter V, followed by the from node to the reference node. If we add node names to our schematic, we can see that the voltage of battery V1 is VAD and the voltage across R1 is VBC. For naming currents, the letter I is used. For instance, we can say that the current flowing through R2 is I5. Now that we know that each electrical element has a symbol and a name, we're ready to look at the last important characteristic, its value. The value of a component is simply a number that describes its electrical magnitude. To summarize, all components have a symbol, name, and value. An example would be a 1.5 volt battery. Each parameter, such as voltage, current, and power, has a name and a value. We keep on mentioning voltage and current, and by now you must be wondering what our obsession is with these two. The reality is that any component, no matter how big or small, can be fully described by its voltage and the current flowing through it. Suppose we have a component and we don't know what it is. It's just a box. We usually refer to that as a black box. This black box has to have at least two electrical connections. Each of these connections is called a terminal, and each terminal connects to a node in the circuit. Even though we do not know what this box is, we can fully describe it, electrically speaking, by figuring out its voltage across the terminals and the current flowing through it. For our black box, if we connect one terminal to node A and another terminal to node B of a circuit, then we can describe its behavior by finding the voltage VAB, the current coming into terminal A, I1, and the current coming out of terminal B, I2. Let's stop for a moment to discuss the polarity of currents and voltages. In our first video, we briefly introduced the concept of positive and negative voltages and currents. We know that if voltage VAB is 1 volt, then voltage VBA is negative 1 volt. We also know that if a current flowing from node A to node B is positive, then the current flowing from node B to node A is negative. It's now time to formalize the sign convention we use in the series of videos. The most common one is called the passive sign convention, which establishes that positive current flows in the direction of a voltage drop across a component. It is important to understand that this is a convention. You could choose the direction of positive current to be in the direction of voltage rise, and as long as you're consistent throughout the circuit analysis, you would be able to analyze the circuit correctly. But we recommend that you stick to the passive sign convention. To demonstrate the passive sign convention, let's bring our black box back. Let's say that the voltage VAB is 5 volts. Then the current I1 is positive because it is flowing in the direction of voltage drop. If we drew a current I3 in the opposite direction of I1, then I3 would have the same magnitude of I1, but its polarity would be negative because it is flowing in the direction of voltage rise. If we now flip the polarity of VAB to negative 5 volts, then the current I1 is negative and I3 is positive. The importance of the sign convention will become clearer when we look at the concept of power, so let's dive right in. We hear the word power many times in all sorts of situations. The news talks about the power of politicians to create change, movies highlight the power of superheroes, and environmentalists urge us to be power efficient to save the planet. In general, power is the ability of someone or something to do or achieve a task in a given period of time. In the electrical sense, power refers to two different but related things. First, power is the measure of what components consume to function properly. A light bulb requires a specific amount of power to illuminate your room. Different components require different amounts of power to do their job. We can see this effect with our electric bill. If we leave a fan on the whole month, we will receive a lower electric bill than if we leave the AC on for the same period of time. This is because the AC requires more power to function than a fan. When you flip the switch in your house, power is delivered to the light bulb and the light turns on. But where is this power coming from? This question takes us to the second reference of power in the electric world. For a component to consume power, another component must generate it. In your house, you receive power from a power plant. The power plant in turn charges you for the amount of power consumed each month. But we don't need to think about massive power plants to find a power generator. In our example, we used one battery to power one light bulb. The light bulb is clearly consuming power to generate light, and the battery is providing this power for the light bulb to function. Just like different consumers need different amounts of power, different generators are capable of generating different amounts of power. When a component like a battery is generating and delivering power to the rest of the circuit, we say that the battery is sourcing power. When a component is using power to do its job, like illuminating the room, we say that the component is sinking power. This is just common lingo that you should know to sound smart in front of other people. Power is measured in watts. Instead of using the word watt every time we write a power number, the letter W is used, just like V is used for volts. For instance, the light bulb consumes 5 watts, or simply written 5W. Let's look at how power relates to the two fundamental parameters of electric circuits, voltage and current. We said that a circuit is fully described by the voltage across its terminals and the current flowing through it. By this logic, power, a characteristic of a component, must also be described in terms of voltage and current. Power is the result of the multiplication of the voltage across a component and the current flowing through it. It may not be easy to see why we need both to describe the power sourced or consumed by a component. Let's think about a sprinter who needs to run 1,000 meters to win a race. There's two characteristics that will determine the performance of the sprinter. The first one is his or her muscle strength to run. A weak runner would have trouble winning the race, but no matter how strong the runner is, if his or her stamina is low, it will be hard to make it to the finish line. A sprinter needs both strength and stamina to compete. You can think of voltage as the strength of a component and current as its stamina. In order for a light bulb to illuminate a room, it needs both strength and stamina. The more strength the light bulb has, the brighter it will illuminate. The more stamina it has, the longer it can keep converting electric energy into that light. We have a mathematical derivation that shows that P equals voltage times current. We have added this in the related content to this video. By now you have realized that we like analogies to explain concepts and use examples to show their applications. Here's an example of power. Let's connect a battery to a light bulb. The first thing we want to do in the analysis is convert the components to their symbols. Now that we have a schematic, suppose the battery generates 1.5 volts, then the voltage VAB is 5 volts. Let's say we measure the current going through the light bulb, and we then find it to be 1 amp. Remember that all parameters have a name, so let's name the current IAB since it's flowing from A to B. Then power PAB is the multiplication of VAB and IAB, or 5 watts. A side note before we continue. All units in electric circuits follow the metric system. So if we have VAB equals 5 volts, then it's true that VAB equals 500 centivolts, 5,000 millivolts, and so on. We said the importance of the passive sign convention will become apparent when we talked about power. So let's keep that promise. If we have a black box named BB1, and we connect it to another black box, BB2, how do we know if BB1 is a power consumer or generator? Assuming that the circuit works correctly, we know that one black box is sourcing power while the other is sinking it. But which one is the generator? We cannot measure power directly, but we can use a voltmeter to measure voltage and an ammeter to measure current. So let's say we measure the voltage VAB equals 5 volts and the current I1 is 1 milliamp. BB1 and BB2 form a closed loop, so the current I1 flows from the positive terminal of BB1 into the positive terminal of BB2 and leave the negative terminal of BB2 into the negative terminal of BB1. Let's do some power calculations. We said that P equals V times I. For BB2, the voltage across its terminals is VAB equals 5 volts. The current I1 flows from the positive terminal of BB2 to the negative terminal of BB2. By the passive sign convention, the value of the current is positive. So I1 through BB2 is 1 milliamp, and the power is simply 5 volts times 1 milliamp equals 5 milliwatts. Now, for BB1, the voltage across its terminals is also VAB equals 5 volts. But the current I1 is flowing from the negative terminal to the positive terminal of the components, so the convention tells us that the value of the current is negative. Power for BB1 is then 5 volts times negative 1 milliamp equals negative 5 milliwatts. If we follow the passive sign convention correctly, the power calculation of a component that consumes power will always be positive, and for a component that generates power will always be negative. A way to remember this power polarity is to think of power as exiting a source like a battery and entering a consumer like a light bulb. When the power is transferred from the sourcing element, it is left with less power, hence resulting in a negative value. When a consumer receives power, it now has more to do its job, so the sign is positive. This is only true if you follow the passive sign convention. If you decide to change the sign of current in the convention, then you must ensure that you understand how that change affects the sign of power and all other electrical parameters. So that's it. Now you know that symbols are used to eliminate any conflict of translation in circuit design. Names are used to identify each component and parameter in a circuit. Values tell you the electrical magnitude of a component characteristic. Voltage and current fully describe the electrical behavior of an electrical component. The passive sign convention indicates that the direction of positive current is in the direction of voltage drop. Power equals the multiplication of voltage and current. In a circuit, we have power sources and consumers. Power follows the passive sign convention. A positive power calculation indicates the component is a consumer, and a negative power calculation indicates that the component is a source. You're one step closer to designing the next computer. Keep it up, and thanks for watching.